Hello everyone. The title of our paper is PAPR reduction scheme for localized SC-FDMA based on deep learning. I will present our research in the four parts: introduction, methods, results, and conclusion. Well, the single carrier frequency derivation multiplexing access has been adopted in the long-term evolution uplink. It can be described as a version of orthogonal frequency derivation multiplexing in which precoding and inverse precoding stages are added at the transmitter and the receiver ends respectively. SC-FDMA has similar throughput and complexity as OFDM. However, the peak-to-average power ratio PAPR of the localized SC-FDMA is still large. It requires a large input backoff of the transmit hard power amplifier from its output saturation point, which leads to very low power efficiency. Although many techniques are used to reduce PAPR, the spectral efficiency and the computation complexity are still needed to be improved. Recently, deep learning, an important branch of machine learning, has shown great potentials in optimizing wireless communication system. As a pure data-driven method, the features and the parameters of a deep learning model can be learned directly from the data without handcraft or ad hoc designs by optimizing an end-to-end loss function. In autoencoder system, the transmitter and receiver of end-to-end learning-based communication systems are both represented by neural networks. An autoencoder consists of autoencoder and autodecoder, which corresponds to the transmitter and the receiver in communication system respectively. Where the analog between autoencoder and communication system has been used in many publications. Well, in this paper, we introduce deep learning not only to reduce high peak-to-average power ratio of SC-FDMA, but also to make it more robust to the nonlinear distortion caused by the high power amplifier and filters. Well, the second part mainly focus on our main methods. First of all, we give the system model in figure 1. Beta here is binary information. The signal is obtained through modulating the binary information. Then the signal is nearly pre-coded by an n by n DFT pre-coding metric. Then the signal is converted to the frequency domain, where the resulting frequency domain data vector are mapped across the frequency band by localized method. And then the frequency domain elements are processed with a k-point IDFT and converted to the analog domain. Finally, the signal is fed to filter and high power amplifier. We can see after the receiver receives the signal and performs the inverse steps to recover the binary information. Well, the final transmitted signal is given in equation 1. We can see that the transmitted symbols can be corrupted by the high power amplifier. The term means the corruption caused by the high power amplifier and the band limit filter here. Well, to achieve an efficient SC-FDMA system, we introduce autoencoder to optimize the transmitter and receiver jointly. In other words, we want to introduce the autoencoder to make the transmitted symbol less affected by the high power amplifier and the band limited filter. Okay. The proposed scheme is shown in figure 2. Overall structure of proposed AE-SC-FDMA is shown. Or here AE is the autoencoder. It consists of 3 modules, namely the transmitter, the receiver, and the channel. The transmitter takes the modulated symbol S to generate the transmitted signal. Since PyTouch cannot operate with complex values, S is split into real and imaginary parts. Then the input vector for the encoder is reconstructed by concatenating the real and imaginary parts. Then the vector is fed into encoder block. After the encoder outputs are fed through SC-FDMA modulation block. Well, this modulation block mainly covers the performance shown in this figure. Well, then the vector is fed into channel. Well, we give the final transmitted signal in equation 2, or the received signal pass through the demodulation block. Similar to the encoder, the symbol should be divided into real and imaginary parts. Here, the obtained vector is fed into the decoder, which is composed of the autoencoder. Finally, the recovered symbol is given in equation 3. Here, xt is the transmitted signal. H means the effects of channel and demodule, and here this means demodulation, and G is a decoder. Well, the encoder and decoder contain the subblocks with the same structure. Each subblock contains fully connected layers, bench normalization, and activation function. Well, to optimize both the transmitter and the receiver performance on the hard power amplifier and the filter effect, we jointly train the model to adjust the encoder block and decoder block, respectively. 2 objective functions required for network training are provided, and a loss function for network training is proposed based on these objective functions. Firstly, to make signal be robust to the nonlinear amplifier, the first objective function is set to minimize the distance between recovered symbols and the original symbols, which is given in equation 4. Whereas the first objective function is minimized communication receiver are more likely to obtain the correct communication information. Secondly, the transmitted signal is expected to have lower PAPR. We propose to minimize PAPR as a goal. Then the second objective function is to minimize L2, which is given in equation 5. Thus, to jointly train the two modules, the joint loss function is divided in equation 6. Well, omega here is denotes the weighting of the second objective function. Well, the third part is about our results. The parameter setting is given in table 1. Or PAPR performance comparison is shown in figure 3. The PAPR measure is commonly used as an indicator for the required amount of IBO for HBA operation. Thus, a low PAPR value is beneficial for the efficiency of the high-power amplifier. We can see that compared with SC-FDMA, the proposed scheme achieves about 2 to 3 dB. For SC-FDMA with SLM, the gain is about 1 dB. Moreover, for CAE-SC-FDMA, AE-SC-FDMA outperforms about 1 to 2 dB. Thus, the nonlinear distortion is expected to be smaller and the power efficiency can be improved in the proposed AE-SC-FDM scheme. Well, next we show the BER comparison. Well, BER performance comparison of these schemes in the AWGN channel under IBO under 0 dB IBO, where is shown in figure 4. The BER performance of the AE-SC-FDMA is obviously better than that of other SC-FDMA schemes in the entire SNR range. Compared with original SC-FDMA and SC-FDMA with SLM, proposed scheme outperforms significantly in the entire range. Besides, compared with CAE-SC-FDM, the proposed scheme achieves about 5 dB performance in the low SNR range. Well, in conclusion, this paper proposes a novel autoencoder-based PAPR reduction scheme for localized SC-FDMA, through optimizing transceiver jointly based on deep neural network. AE-SC-FDMA is capable of reducing PAPR while improving robustness to the nonlinear effects of high-power amplifier. Future work will focus on the usage of sparse autoencoder.